Alright, I thought I'd just do a quick video on differential equations, just because maybe you didn't do specialist at school and maybe you're thinking, well, these differential equation things are really messing with my head and they're difficult and hard. And oh, they are, because people write whole books about them. You get big thick books on how to solve some particular sort of differential equation, and they get names like linear, first order, second order, separable, partial, all sorts of complicated names, which is just people classifying them according to their properties. But it sounds scary to start with. So let's have a look at equations. Let's recap some equations. X plus 7 equals 11. Solve for x. Okay, well, x equals 11 minus 7, x equals 4. So there we are. We have a simple equation with one variable x, and the answer is a single value 4. Pretty easy. Alright, what about x squared plus 4x plus 3 equals 0? Okay, so this is a second order quadratic equation. So let's do that. Okay, so this one, we know we can write it like this. So we can write it as x plus 3x plus 1 equals 0. And we know that in order for the product of these two things to be 0, that'll be true if either this is 0 or that is 0. So we can say, okay, x equals minus 3 is a solution there, and x equals minus 1 is a solution from there. And if we choose one of these values, x equals minus 1, and put it back in the original equation, we get minus 1 squared plus 4 times minus 1 plus 3, which is equal to 1 minus 4 plus 3, which is equal to 0. So we see that that is indeed a solution. Okay, what about if we have x plus y equals 11? Well, same as above, x equals 11 minus y. So if you tell me a value of y, I can tell you the value of x. Okay, so we might want to write this instead as, say, look, we've got a function f of t, say, plus t equals 11, and then we can write f of t equals 11 minus t. In other words, for this equation, for any value of t, I can give you the function is given by 11 minus t. So now we have, instead of one solution there, two solutions here. Now we have an infinite number of solutions depending on what this value t is. Now, there's some nice simple differential equations that you saw in high school and all of you got very familiar with, and they look like this. Very simplest of differential equations. They go like this. You have a function x of t, alright, and what we want is it to satisfy the following. We want d squared x dt squared is equal to some constant a. And let's solve this differential equation. Alright, if the second derivative of x is a, then the first derivative, dx dt, must just be equal to a times t, because if I differentiate this side, I'm going to get a times t. Differentiate with respect to t just gives me a, which is what I'm supposed to get, and so differentiating this gives me that, and that gives me that. But it's not quite the whole story, because if I add a constant to here, like that, and I differentiate now, when I differentiate that, it goes to 0, so the derivative of this is just a, and the derivative of that, of course, is that. So it's still good. There's my solution. Now we want to solve for x, so we need to do this once again. So okay, so x of t is equal to, we need something which when we differentiate it gives us a t. So if we go a half a t squared, if I take the derivative of that, the 2 will cancel out with a half and I'll just be left with an at. Plus, now we've got this v naught, so if I just v naught t, then when I take the derivative of that, I'll just give v naught. And just the same as before, if I add a constant and I take the derivative of that, I get nothing. So it's still true. Okay. So you recognise this equation maybe. X equals x naught plus v naught t plus a half at squared. It's the solution to the differential equation d squared x dt squared is a constant. The v naught and the x naught, as you know full well from high school, depend on some or other conditions associated with the problem. You're saying that the initial position, it started at x naught equals 3 meters. Okay, you're saying its initial speed, v naught, was minus 7 meters per second. These were maybe given to you in the problem. So these are constants occur because of particular things in a particular problem you're dealing with. Often they don't matter. Alright, so far so good. One last level of complexity. Let's say we've got a function f of t, and we've got d squared f dt squared, not a constant, but equal to minus omega squared f. Now, I'm not going to ask you to solve this. In your assignment you've got some problems to do with differential equations. They also don't ask you to solve them. But let's see if we're told that a solution to this differential equation is f of t equals a sine omega t. Let's verify that that is a solution. Okay, so in other words, let's take the first derivative, and that's going to be a omega cos omega t, and let's differentiate again, and if we differentiate again, we're going to get that this is derivative of cos is minus sine, so we're going to get minus a omega squared, because omega times omega, sine omega t. And if we look at this, we can see that the a sine omega t is there, so it's minus omega squared times f of t. Okay, so we've shown that the second derivative of this function is indeed minus omega squared times the original function. So we've shown that this there is a solution to that differential equation. It turns out it's not the only one, not by a long shot, and you'll notice that it's a solution no matter what the value of a is. So just like in other equations, sometimes there's a lot of values which will work, but equally well we could have started off with f of t equals a cos omega t, and you can verify that if you differentiate that twice, you'll also get a solution. And if that's a solution, then it turns out that of course f of t is equal to a sine omega t plus b cos omega t is also a solution. So there are lots of possibilities. that will be a solution for this equation. Okay, so I'm just hopefully tried to make you see that the differential equations are not really horribly messy and complex. They can be difficult to solve, they can have lots of variations, but to verify that something's a solution is straightforward. In the assignment, the problem is maybe a bit more difficult in that it's rather messy, and so you've got a lot of algebra to do to show that a certain thing is a solution, and it's not quite as straightforward as this. You don't just come out like as easy as this in the solution, but it's the same process with a trick or two. Okay, so I will leave that there.